Yeah, thanks for having me here. My name is Kraska. I'm a professor also at CSAIL. The main area I'm working on is either applying building systems to make machine learning easier to use, or making systems in general easier, or the other way around, applying machine learning to systems to normally make them faster. So for this talk, I will give you a little bit of an overview of both of them and how they look like. So starting with the first one, on how to apply machine learning for systems. So why are we doing it in the first place? The core idea is just you probably have seen a plot like this, that most, you stole it, perfect. That Moore's law is coming to an end, right? It's the speed and how we improve processors is slowing down. Now, if you contrast that to the pace on how data is actually increasing, we see that there's soon more and more a mismatch between the two, right? We don't innovate on the hardware front as fast anymore, and we produce more and more data over time. So what we are wondering around is how do we address this? And one way to do that is actually specialization. Right? And we see that already happening on the hardware front, like GPUs, TPUs, FPGAs, and so on. What we are asking ourselves is, can we not do something similar for systems? Specialize them more to give you better performance in the end. Okay? So for that, it's like creating your old times of questions. Okay. They have a whole bunch of pop-ups regarding the keyboard or some other stuff. So in regard to adjusting systems automatically more, specializing them more for better performance, there are different levels of specializations you can do. The most basic one is if you have a complex system, they already have a bunch of knobs. Right? So if you take a database, you can decide what indexes to use, how big the buffer pool should be, page sizes, and so on. The trend is that these knobs are now being automated in the sense of there's a mechanism in place which observes the workloads and tunes the knobs for the workload and makes the system through the knobs more specialized to a workload. However, we want to look beyond that. And for a long time, we looked into what we call learned components, how to more deeply embed machine learning into a component to even specialize it further and to give even better performance. And I will give you some example of that. And then ideally, eventually, we want to build instance optimized system, take an entire system and optimize it to the workload for better performance again. So starting with the second one, the learn components part, we see actually these things are currently slowly being adopted. Google Bigtable took one of our ideas and integrated it. To give you a flavor of what does it mean to pick a component, take a typical database. It has a bunch of different components in order to get the overall functionality of retrieving data fast. For example, indexes, query optimization, sorting mechanisms, and so on. Some of them, if you look at that, they are very fundamental algorithms or data structures. Right? An index is a very fundamental data structure. Right? Here, I will just focus on a few of them. And each of these components we actually did some work on them. But there are many, many other people by now which do work in this area. So we are not the only ones. Let's start with indexing as an example, because it's one of the simpler ones to grasp. So an index is a fundamental thing in most transactional systems. It's a fast way to find a data item. I always compare it with finding a book in a library. So let's assume you're looking for a specific Harry Potter book, right? And you have a big library like that. How do you find the book? One way to do that is actually consulting a catalog, right? You have this little index cards. They are alphabetically ordered, let's say by title. You look up the right index card for the title you're after, Harry Potter, book 1. And then eventually it gives you a pointer to the location inside the library. If you have a very large library, those are normally organized in these drawers, and you might have a whole room of these index cards. Right? So how does now finding a particular book look like? It's first, if you go for Harry Potter, okay, I need to go to the age category there. Then you drill one further down, you get to the right drawer, and eventually you get the index card, and this gives you the location. Right? This essentially is what a B tree does. It's exactly the same thing. It narrows it further and further down until you get a location, typically a pointer on disk to a page or a block. Right? However, there's an alternative way to find something in a library, and that's probably more common for people to do, is you just ask the librarian. Right? Because the librarian knows roughly how the books are organized, and he will tell you, oh, the children's book are in this corner up there, and you can just go there. Because he has a mental model about how things are distributed in his library. Even though it's not perfect, it's good enough that it points you in the right direction. Then you do a little bit of localized search, and normally you find it. Right? Even better, he can organize the library in a way that it better fits the access patterns and his mental model. For example, if children's books are frequently visited, why not put them in a more prominent spot? Right? So in the end, that means like instead of having this like index cards, we replace them with the librarian. Right? Which is like a model, it's rough, like an approximate structure, but it still gives you the final result back as well. So what we were wondering ourselves is just like, can we not do the same for a B tree, which is the traditional index structure used in a database system. Right? So to give you a very, very simple example on how that might look like, let's assume like we have this table here of orders. There's an order ID, they're just increments, very, very common. And now you want to look up an order by order ID. So you're after this column here in the beginning. Also for simplicity, just assuming that everything is in my memory and that everything is sorted by the ID column for now. Right? These are assumptions we can relax later on. So if I have this ID column, of course I could now create a B tree over it to look the right ID up. And this is actually what most transactional systems would do nowadays. However, if you look very carefully at this column, you also notice they are just increments. So in order to find actually position inside this table for a particular ID, the only thing I need to know is like the first ID number, right? And then I take the ID I'm looking up, let's say 1010 minus 1000 gives me an offset of 10, and I know at the 10th position I find my record I'm looking for, right? Because I know all of them are increments. So I can transform this complex B tree structure to something very, very simple, which is an array lookup. Very, very faster, of course, right? So let's make the example a little bit more complicated and just say, like, instead of looking up by ID, we want to look up by date. Right? And dates are not as nicely. They are not just increments. They might be distributed. We have several orders on the same day, and so on. Right? So how do we do it in that case? In fact, it turns out that you can use a very, very similar idea, but now the model comes into place. So let's assume, again, everything is ordered by date here, an important assumption. So what we can take is like the date column and build a CDF model over the data, which gives me the probability mass for any given date on how many orders are below that date. If I take this probability mass now and multiply it with the numbers of records I have, I can again do an offset calculation. Right? So I model all the dates I have using a CDF model, and what model to use is completely up to you. And then I take that CDF model, ask for the probability mass to a given date, and I can get an offset computer. If the model is perfect, that's the only thing I need to do, and done. If the model is not perfect, given that I know all the dates are actually sorted, I do a second step, which is like some localized search, almost like in the library. And then it just returns me the orders with the particular date I'm looking for. The nice thing about that is 100% guaranteed to give you exactly the same guarantees like a normal traditional B tree. Right? It's just like if the record exists, it will be returned. It's not like that suddenly it becomes a fuzzy data structure. So you might ask, like, okay, what types of models to use for that? And it just turns out, but like whatever works. What we found is like we created this like idea of like a recursive model index. You can think of it as like a mixture of experts, which works particularly well to approximate the CDS functions with certain types of guarantees. So in the end, like we replaced the B tree structure with a model, and we did evaluate it, and we found some interesting insights when we did that originally. It's just like compared to traditional data structures, and here we are only comparing read-only data structures for the moment. I haven't even talked about inserts yet. The learned index one actually performs very well. So what you have here on the x-axis is like the lookup time. The y-axis is the index size per se. And then we compared learned index here on the left with other alternative state-of-the-art approaches, including FAST, which is like highly SIMD optimized read-only index structures, lookup tables, interpolation search, and others. And overall, what we see often is that like we are orders of magnitude smaller in size and like roughly 2x faster in lookups for certain types of distributions. By then, like this result actually has been confirmed by others, and this is one benchmark studies. By now, I'm aware of like 5 different benchmark studies which do nothing else than looking into when does it work, when it doesn't work. People have worked on like theoretical guarantees around that, and it turns out that you can actually prove that under certain conditions, those are faster and smaller. People added support for inserts and transactions, and this is just like over the outdated list of papers. There are even more by now. People have tried to integrate that into different systems, and there's a big question, like, does it actually matter if you're a little bit faster? And the answer is actually it just depends, right? Like in some cases, just like I told you, it's like the 2x faster, but it's nanoseconds faster. Does it matter in a big system? It does if you invoke the index, for example, in a closed loop. What it actually turns out is just like that the index size matters more. And there are like 2 results here. One is Bigtable introduced that, and their indexes tends to be so big that it doesn't fit even on a single machine or on a single block. So with that, they were able to compress it further, and they save 1 I/O to Colossus, the internal storage system, which gives them a bump of like 1.5x in many cases. People also integrated that into like key value stores and other things. And the reason why you see these speedups are mainly, again, because the index is smaller, not necessarily that the lookups are faster. What I found more interesting about this result is actually how people started to leverage the same idea in different contexts. So as I started out with just like this idea of like an index structure versus ML enhanced or learned, it's just like it's a very like general purpose data structure. You cannot just use it in a database system, but you can use it in very different other places as well, and people have. So here's just like a list of different papers which like took this idea and applied it in a different context, from sequence alignment, networking packet classification, to like various other domains by now, and just like for example, spatial indexes, and vary that in various ways, just like this core idea of like, okay, let's approximate the data using some type of a model and take then advantage of it with your like other algorithms and data structures around that. So like the key insight here is that you can model your data distribution, and if you have this model of the data distribution, you can design your data structure or algorithm differently. Very related to this, like this is also one of my like favorite like toy projects to some degree. It's just like you can take the same idea to also improve sorting. So let's assume for the moment you have a very cheap way to create a model over your like keys you would like to sort, right? Then you could, in theory at least, use this model F and just look at the key and put it directly into the sorted order, using, again, this model of the CDF function. So there's no additional step. If this model would be perfect and cheap, you can just like go over all the keys once and put everything into place. So it's like O of N sorting. Very, very similar to radix sort, to be honest, right? Because you also, with radix sort, you look at like a certain numbers of bits, and then you put it directly into place. But normally, radix sort is highly sensitive to the domain size, right? Like how big or long your keys are. In this one, in theory at least, it's not. So you could do this, and then you could achieve O of N sorting, assuming, of course, you have this model in place. And this might be particularly useful for applications where you have to sort over and over again. Let's say Google's web index. And then if you're, in case the model is not perfect, you might have to do some correction step. So we tried that even with the perfect model. So we just assumed like we just want to sort something very cheap, and we created a model which was like has 0 overhead. And to our surprise, it works, but it's definitely not faster than even the typical n-log sorting algorithms you might find. And part of the reason is that like modern sorting algorithms are highly optimized that they avoid random memory access. So they do this like sorting of sub-pieces so that everything stays in the CPU cache and you don't have to go to main memory. It's like if you do this, you can see every single time you apply this model function, you point to a different location in main memory, and that kills you in the end. So we created a variant of it, which is just like essentially uses this idea of CPU cache. So we do several passes, but then in each pass, we are careful that everything only happens in the CPU cache. And then we do first like a coarse grain sort over the data, and then we pick it up again, do a fine grain sort, and then a bunch of other steps in it. If you combine all of that, we actually show that we can beat the next best sorting algorithm, and currently the best we were able to find is IS40 by roughly 30% in sorting throughput, which is pretty nice for in-memory sorting. We also went then the next step and said, like, okay, there's an official sort benchmark. Can we beat that? And like this is some result from last year where we actually implemented the learned sorting algorithm using that idea to get the most energy efficient sorting available right now according to the sort benchmarking website. Right? So we extended that for external sort, and now if you see about like kilojoule per key sorting, we're actually dominating it. And ELSA here, that's our solution. On the far right, whereas on the left they're like the previous winners of this like category. We also wanted to do the big sorting category, just like the general sort, but like we couldn't, unfortunately. It became a pure hardware game by now and requires like big cloud resources. Okay, so this is just like two flavors of like learned sorting algorithms. As I started out with, there are a bunch of like other components, data structure algorithms which are used, and we looked into them and tried to figure out how to make them also ML enhanced. However, what we were always really after is like, how would they come actually together? Right? And for that, we started a project in the end called SageDB. It's based on the observation that like this is a typical database architecture diagram from Hellerstein and others. That when we looked at it, that we actually found that each of these components in this architecture diagram getting actually ML enhanced. Like access methods is like what I talked to you about in the beginning with B-trees. People worked on like scheduling, including us. Query optimization, we have a bunch of projects on it. Buffer manager, log manager. Each of them here in blue, I can at least name one paper which tries to make it ML enhanced. What's missing so far is how the thing's actually coming together. Because we actually observed that in many cases, like if you optimize one component, maybe something else might suffer from it. Right? So we went to this journey and tried to build like a full instance optimized system, which is called SageDB. These are like, unfortunately, I don't have time to go into much detail here. There's like a bunch of different components. We developed, the core idea was like to improve the data layout and co-optimize it with things like materialized views. We achieved some like very promising results on it. And like this is comparing SageDB here in regard to latency and like the total like database size against Postgres using standard tuning and having an expert tune it, and then a commercial analytical database. And again, with standard tuning and expert tuning. And what you see is just like overall SageDB does pretty well at like not the smallest like in-memory storage cost, but like pretty close to it. We had this prototype. When we got the result, we actually decided like to build a company around that. And that's the reason why we haven't continued at MIT with it. But like, there's this big question, it's just like a company's now adopting this type of technology so far as it induced. And the nice thing is since last like November, actually I can say like magically our company we started disappeared, and now we are suddenly all at Amazon. I cannot tell you who acquired us, but if you look at my affiliation, you might guess. And we released this feature last November, which actually takes a bunch of these ideas, and now it's in preview right now for Redshift. Right? If you want to learn more, there's a link here at the bottom which points to the keynote where they walks through the technique and how the system is actually adopting now and uses these ideas actually in practice. So we are getting there even now in the commercial environment. Okay, sounds good. So like I think there's still, like even though like now slowly we're finding the things in like commercial system, I still think there's a lot to be done, and I always compare it with this, like you have a traditional component, you just think like, oh, let's make it a little bit more customized by applying machine learning to it, and then the moment you get started, you actually discovered, oh shit, that's a much deeper problem than I thought it is, and it takes a while until you come back to the surface and actually make it work. It's even harder if you want to make something work which actually is deployable, because there are all these corner cases, robustness, guarantees all play an important role. But it's a really, really fun area to work in. I think given the time, unfortunately I will skip over the system for ML part, even though there's been also some interesting announcements. Just finally, we want to give a big shout out to all my students and postdocs. All the credits belong to them. And with that, I'm happy to take additional questions.